in there. But let's move on to the second part of the lesson, which is network analysis in Python. So those of you who have taken the introduction to advanced geoinformatics at least have done these network shortest path routings and OD matrices using ArcGIS network analyst. So the basic idea is familiar to some of you. I'll just show again as a motivation. This is a web map developed by Joose Helle. Some of you might know him. That looks like this, and the idea here is that if I can use the current location, so it asks me to locate myself based on the IP address, and then if I would want to go to, we are actually today have to admit that moved the lesson because we're going to Löyly, Löyly with the research group, so duties. So I want to go to Löyly later on, so I can find the quiet path or the clean path. Oops. Maybe. So what this tool that Joose is now developing in his master's thesis, mostly based on skills he learned on this course, that's what he said. He's also skilled with JavaScript for visualizing the maps. So there are different routes based on the, quietness, so the noisiness. So there's this data set provided by the city of Helsinki about the decibels in different, I think it's kind of a polygon layer. Then he also has matched those decibels to the street network, so per each road segment. And then it calculates the routes from A to B, so there's an origin and a destination node here. And then it recommends the routes based on how noisy they are. So the red one is the most noisiest, might be the shortest in terms of the distance, and then the greener, then the more quiet the road. So there is this kind of routing problem to find the shortest path, but then we can also add a cost, and in this case the cost would be the noisiness of the road, kind of the one of the paths. So then it kind of becomes more costly. So we can have a graph, again, nodes and edges, and then the graph can have some weights. So then it becomes a weighted graph if there is some cost for going through a road segment. And in Joose's application, it is then the quietness, or then vice versa, the noisiness, or it could be the speed, based on the speed limits, the time to traverse through one road segment, and so on. So this just as a quick motivation and as an introduction to the analysis approach that we will kind of roughly go through. So when solving these shortest path problems in networks, we use specific network algorithms, and then this Dijkstra's algorithm is quite popular, and then this A* is an extension for the Dijkstra algorithm. I had planned to do a brief introduction to Dijkstra's algorithm. We can see how that goes. But basically, when you then go see the documentation of OSMNX and then NetworkX, these shortest paths tools, so Dijkstra is one of those algorithms that we can then use for solving this shortest route from A to B, including some weights in the network. So this is the documentation from NetworkX, which is yet another function, but what is it based on is then a Python implementation of the Dijkstra algorithm, which would then look like this. So there's a little, well, not a little, quite a long doc string for this algorithm. So it's defining the Dijkstra algorithm. There's the G stands for the graph. And when starting to solve this problem, we always have some start node in the graph. You can read this more carefully if you want. And then the main idea of the algorithm is that it kind of visits each node and checks how long was the path to that node, and if it was the shortest path, then that is the solution. And it keeps track of the visited nodes, and then for each node the kind of path to that node in a way. But that is what is then behind these tools that we are using from OSMNX. And again, Dijkstra is then only one of these available algorithms, but if we have a network with weights, then by default, then the more simple tool we are using is then using this Dijkstra algorithm. So that just to give you a bit more background on these approaches. Just also go from here. So moving on to the new notebook, and let's import the modules. The module names are in there. I think you should, if I don't remember wrongly, when you import OSMNX, it also, or when you install OSMNX, it should also install Network X on your machine, and then the other packages are already familiar from the previous weeks. And then we'll do again this step that caused some problems in the first lesson. So let's fetch the network so we can analyze it. And this time, if you didn't already do it, so graph from place, we'll use Kamppi as we did previously as the query. So let's restrict our query to the drivable network. So there's also then other types of there's different types of network types available. So if you want to analyze the walkable network, you can define network type equals walk. Then there's bikeable network type equals bike, drive, service roads. The all private was the default one. So this just to give you ideas on further application cases. So graph from place name query, network type drive, and then we can again OX plot graph. So this is now the OSMNX plotting function. And what this actually does, we could also write it as it is in the lesson materials. So this uses then matplotlib and returns a figure and axis object if we would then using this syntax want to plot other features or layers on top of there. But just to check that we are seeing something that looks like the street network of Kamppi. I hope this probably went now through with everybody. Yeah, no network connection problems. So then, again, we could retrieve the nodes or the edges from the network. So graph to geodata frames. Function that we used earlier, input is the graph, but if we only want, and remember it returned these two different data frames, but if we want, we can set nodes equals to false, and then edges equals to true. So in this case, it only then returns the edges. Oops. Graph. So there's some information related to the edges in our network. For example, max speed, which is then the speed limit, if it has been recorded, the length of the line, which we will eventually use as the weight in this example, and then the geometries as lines, strings, and so on. And let's now finally check the CRS. AutoGIS. So it is VGS-84 latitude, longitude. So you remember, if we want to then talk about distances or make nice maps from Helsinki, we want to have the data in a projected coordinate system. Let's still furthermore check the data. So the line strings were there, and also from the coordinates we can confirm the CRS. Yep, I am recording. And then there is further information if you want to dive into all these details of the road network, of course, depending on the area where we fetch the data. So there are then links to these different explanations of these different columns. For example, the highway tag contains the street network type, and those who have been mapping, for example, road networks from sub-Saharan Africa know this tag very well. So we could have, for example, it can be just highway, yes, that it is a road, but then there are multiple different, it can be a secondary road, a residential road, depending on the road type. And then this max speed indeed is then the speed limit if it has been set. So for example, in Mäkelininkatu, at least based on this, it's 40 kilometers per hour. Yep. So let's have a closer look at this highway column before we go into the analysis. So I showed this value counts function, which is quite useful. As I mentioned, if you also have no data values, you can check with value counts or isnal.value counts. But we have mainly residential roads, primary roads, and so on. Some that they are roads, but there is no road classification, so unclassified. But these look like that they are parts of the network meant for cars as we wanted to. And if you would then specify network type walk, you would have different types of road tags in here. So then continuing with the projection, so in OSMNX there is this project graph function. And let's store that in a new variable, which is still this network X multidigraph data type, but a projected one. And let's see what we get. Can add a new cell or plot it in the same one. So OX plot graph project. So here, as we have such a small area, you can't really see it, but it has been projected. We can maybe more easily see it if we again fetch the geodata frames. So sorry if I'm going too fast. So the key thing is that you do this OX project graph and store it in a new variable. You can skip the plotting if you didn't have time to do that. Then I'll just maybe do so that I get more stuff on the same screen. And then I'll do this OX graph to geodata frames S. Graph proji, and let's this time take both the nodes and edges. So I could have nodes proji and edges proji in the correct order. So again, I get two data frames from this function, store them in new variables, and then we can check edges proji. Oops. Dot CRS. So now it's still using the VGS-84 datum, but we are now in a UTM, Universal Transverse Mercator projection on the zone 35, which is in Finland. And what does this mean? Is that now we have our data in a metric system, so you can see that already from the line strings that we have in the geometry column. Reduce a bit that. And then finally, with the tools that we are familiar with, we could check using this CRS class from PyProji. If you do like this, so you give the edges proji CRS as an input parameter for the CRS object. You can check what that gives. Gives a bit more information, but at least to me the EPSG code is often quite interesting. So if you would do that, so first we use the OSMNX project graph tool to project the whole graph. Then we took the nodes and edges from there, checking the coordinate system. We know that it's now also the coordinates have been transformed. And then finally, if you check the EPSG code of this coordinate reference system and Google it, so we can confirm that it's now in a projected coordinate system on the UTM zone 34 north, which is then related with this EPSG code. So we haven't used this projection before, but the OSMNX has this inbuilt functions to then project the data to the local UTM CRS. No? No? Is there some questions? Okay, so then if there's no questions about the projections, there's some code cells that will kind of, well, we won't skip, but you don't have to type in. So there's a section about analyzing the network properties, and this is something that is interesting, but you won't need it in the exercise. If you are interested in these network metrics, you can then study this more closely and apply in the final exercise. But there's then some functions in OSMNX, such as the basic statistics, that can be used for fetching kind of these descriptive metrics about the topology of the nodes and the whole network. So there's this kind of basic function which then returns a reduced number of metrics, and now that we projected the data, we can pass that we want, if there's some distance calculations, then they are in the Euclidean space, so on a flat surface instead of kind of these great circle distances, if we would have this lat long decimal degree data. So there's a bunch of metrics, and then there's also another more advanced tool for which we need to make this convex hull, so that we did that in the first lesson. So if you have a set of points as a multi-point like this, then the convex hull is kind of the extent of all of those points, or lines or whatever data. So that's what is happening in there. And we are doing that in order to pass that area. So this more advanced tool then we get more information if we pass that onto the statistics calculations. And these statistics are as Python dictionaries, and what happens in here is that we put them together and then convert them as a pandas series. This is not maybe the core learning content of this lesson, so you can study the code on your own time, but as an output, what we then get is, for example, the density of nodes in this area, average length, total length of street network, and such. So kind of these urban structure metrics in a way. and then also this just basic network metrics, centrality measures as well, closeness, centrality, page rank, which kind of refers to the popularity of a specific node, and so on. So that's and if you get excited about these, there's again Wikipedia helping us to understand the different metrics, so we can talk about these network metrics just in an abstract network, and then of course apply them on this street network, for example, if analyzing the urban structure, and for example then comparing different areas. But I'm a bit jumping over this section so that we can concentrate on the shortest path analysis, which is the main component of this latter part. So let's work through this section together. And this is now it starts from a bit complicated setting, but the main goal is that we have now this Kamppi in here. Kamppi area with the road network like this, and then the road network has these edges and lines and whatever. And I guess let's confirm if I remember right, but we want to, because we have no input data here, but we want to find the shortest path from the centroid of Kamppi. Let's say that it's there. Centroid of Kamppi to the easternmost, like the exit point in the east from Kamppi. So a bit like arbitrary example, but before we can find shortest path, we will define this origin and destination point now in the next code cells. So let's regenerate the convex hull that we quickly already saw in the statistics part. So we'll do that based on the edges. So we'll just kind of clump all the edges, geometries together using shapely tools, and then take a convex hull. So the extent for them as a polygon, could also define the polygon in some other way. This is just to get the centroid, and then centroid equals to convex hull dot centroid. And you can then type in centroid at the bottom. So we should get, let's see, if I would print, just check the coordinates, for example. So we have a point somewhere, should be then the center. So now we have this, is it then I think it's then the origin point. So escape from the middle of Kamppi. Like that. So one shapely point here, we use the shapely tools we learned in the first week of this second period. So then we want the destination point. So let's check what we have in the nodes layer. This is now the geodata frame that we generated earlier. So we have this X and Y coordinates in separate columns nicely provided, and then the geometry column itself, also latitude and longitude, and then the OSM ID of each node in the network. And you can see that the OSM ID is the same as the index of this data frame. So the unique ID for each node is actually quite an important concept in the upcoming analysis. So then the problem would be to find out the node, the easternmost node. And what is that? Well, it's the node with the highest X value, right? Because X is on the east-west axis. If this is now then X, that's Y. So then whatever node is the easternmost, well, maybe it's actually there, will have the highest X value. So that's how we can find the easternmost node in there. So get the X coordinates of the nodes first. So we had this nodes proji column X, right? just to check that. So there's the OSM node ID and then the coordinates in this UTM projection. And then we can take the max from there. So this is the maximum X coordinate in all of these X values. Before that, well, there was, I don't know if that's necessary, but yeah, I think it's not. So we can skip. Let's see if this doesn't work. Then we have to do some data type conversions. So basically, we can then say that max X equals to the maximum value of the column X. There we go. So that's now the X value, and then next we need to retrieve the actual node, so the row from the node's data frame, which has this maximum X value. It might be one or several, let's see. So again, we have this nodes proji, and then we use the lock indexer. Based on some condition, we find rows. So then the condition will be, maybe I'll just do this in two parts. You can maybe do the same. So I added one code cell above there, or you can write it in the same code cell as well. So we have nodes proji column X, and we want to check on which rows the X equals to this max X. And this will be a series with true and false values. Probably there's one row where this is true. So then this will be, I'm just now copying that inside the lock. So that will be my condition on the rows. And with the lock, we can have this condition on the rows and then at the same time select which columns we want to include in the output. So there appears to be only one row where this condition is true, and this is the shapely point object for that row. So we have one point that is the easternmost node. Here we get to repeat some of the pandas tricks, and then finally we will want the X and Y values. So the point object of, well, we want to retrieve the point object from that row. So one way to do it is that we first retrieve the values. Let's check if this works. So this gets a bit cryptic, but if you then take the first value from the values in that result, let's check. So I'll store all of that in one variable and print it out, target. So it should give me a shapely point object. So condition, column, and it's a bit tricky syntax because we could have several results, but in this case we only have one, and we know that there's only one because we checked it, so we can just take the first value from this result as the target point. This may be a bit kind of ugly way to do it, but that's how it is. And why we are eventually doing this is that we will use this shortest path function in network X that I kind of briefly tried to explain here. This is now kind of simplified version as a documentation, but as a parameter it will take a network X graph object, then a source node. So starting node, we had this A node in my example on the table, and then we'll have a target node, and then we'll use some weights. As simple, but if we would then check the source code of this tool, just to understand what's going on, there's a long, again, quite a lengthy doc string. So again, when you will eventually be making more complicated functions yourself, so don't spare words when explaining what happens. But in here, for example, we can check that it checks the source, and if there is no weight, then it uses some other function, but if there is weight, so then it uses this Dijkstra algorithm that I kind of tried to explain earlier. So we now have a weighted graph, and it will end up be passed on to this Dijkstra function. So that's, at least to that level, we need to understand what is going on in order then to control. So the weight we pass will eventually be passed on this, this function in here. But what we are applying in our own code is this just shortest paths function. And now we have the source node, which is the origin, and then the destination, which is the easternmost point. And we can continue with the shortest path analysis. Let's move on. So finally, for these shortest paths, we can see from the documentation that we can't pass a shapely point to this function. We need to have a node, so we need to specify one of these nodes in the network based on the node ID. So the network X doesn't understand anything about, well, maybe something, but doesn't understand our geographic coordinates. It understands the nodes and edges in the network. So a few more further steps. So let's then fetch the X and Y coordinates for the origin. So the origin was the centroid. So we can, using these shapely attributes in the correct order. No, it's X, Y, Y, X. Well, we can name this, well, in the order of Y, X. So we get it right. Same thing for the target. So we are creating tuples. Let's check. Oops, now I'm just copying without thinking. So X and Y and X for the target, Y and X for the origin, which is then the centroid. And we do this in order to find the node in the graph that is then closest to the point. So in this case, the easternmost point will be exactly in the network, but then of course our centroid might be somewhere like not intersecting with the network, and then we need to find the closest. We need to attach it to some of the existing nodes in the network in order to do the routing. So the shortest path happens then in between the network nodes eventually. And then we again use OSMNX. So there is this get nearest node function in a graph. So we use this graph projected graph. Then we pass the origin X, Y. We can check from the documentation soon Y, and then using the Euclidean method. So again, on a flat on a flat surface, the straight line distance. So we will, from this point, the XY coordinates of this point, find the closest node in the network using this OSMNX get nearest node function. So this OSMNX utils get nearest node returns the graph node nearest to some specified latitude, longitude, or XY point. So that's why the order was such, and optionally the distance between the node and the point. And then we use the Euclidean because we have a projected graph. If we would have unprojected graph, we would calculate these great line distances with the hover-sign method. Okay, so, and the output of this would then be the origin node. works, and then orig node. So what this is now, this is the node ID in the networks. This is the ID of the nearest node to the centroid of the area. And then the same thing for the destination, so you can copy that, call it target node, and then we want the target XY with the same method. And now this target node ID should be the same that we had, I think. If I would check now this, just to make a point. So if I take this condition from the nodes proye data frame on index 3, 1, 7, 7, so forth, we had the point, so it was exactly on that node. So we're just kind of, this is kind of not a necessary step in a way, but for the origin, we didn't yet have any node in the network, so that's why we did that. So these are now the IDs in the node layer. Okay. So let's then see what happens next. So let's retrieve the kind of the other information for this origin and destination. The kind of the end analysis will be easy, but how to then interact with these nodes and node IDs is maybe the tricky part in here, so that's why we're spending time. So now we have this node ID, which is also the index of this nodes proye geodata frame. If you remember, maybe I'll just to refresh our memories, nodes proye head. So we have this data frame with the nodes from the network as a geodata frame, points, and then the projected points X and Y, and then this node ID. And now we fetched the node ID for the origin and destination points. So then we get information for the closest node, and then the same stuff. I'm creating a new column, you can, or cell, you can also do this in the same cell. So same for the target information about our target point, the closest node in the network. So then this needs to be target node. So this is now a pandas series. So now we have all the information for those origin and destination points in the network. And then kind of wrapping it up all together so that it makes a bit more sense. So now I have this O closest and T closest. I'll just remove this print so I can fit more stuff on the screen. So we'll put them together in one geodata frame. We have imported GeoPandas at the top, so you can call gpd.geodata_frame to make a new geodata frame. The data will be as a list. We have the origin. So this is a pandas series or a geo series it might be. Then we have this T closest, which we just generated in here. They both have a column called geometry. So we define that the geometry column of this new geodata frame is geometry. And then the CRS is the same as nodes proye CRS. And it will end up having 2 rows of data from these objects. And I'll just store that OD nodes in a new variable, OD nodes. Okay, so there's these previous steps. There's maybe different ways we could end up in this situation of having our origin and destination nodes, but the important thing is to have the node ID in the specific network based on which we will then be doing the shortest path analysis. Yeah, and as previously, the index is the node ID. So finally, we can do the shortest path analysis down here. Output will be some kind of a route, so we can call it route. We're using, try to leave that there, so if somebody's still working on that. So we now will use network X, which we imported as NX, and this shortest path function that we just checked the documentation of there. The G parameter is graph, so we have the graph proji, so the projected graph. Then source, which based on the documentation has to be the node ID, so we have this orig node. Then we have target equals target node, and then we have this weight. So now we'll just put the length of each edge as the weight, but then we could calculate based on the max speed the time to drive through each segment, or if we had a walkable network, it could be based on the average walking speed and so on. That's all of them. Let's run it. I'll put it here in a new column. So what we'll get as an output is a list of nodes. So you remember this first explanation of the thing is that it then remembers the route. So here again, this is then has been the shortest path from origin to the target, and then it's some kind of in some order going through some of these nodes from origin to the destination based on those node IDs. So then using OSMNX, which makes life kind of easy, in here we have a function called plot graph route. Let's also check that quickly. That's now network X. Plot graph route, plot a route along network X spatial graph. Well, and there would be many options to then adjust, but here we will pass on the graph, then the route. So wait, sorry, it's this one here. So then the graph is the network, so we pass the projected graph, then route is a list, so the route as a list of nodes. So we need only the list of the nodes in order to plot the route using OSMNX, which is quite nice. So route, and then we can add orig point equals to orig xy, and then destination point origin, you need to type in origin point equals to target xy. So these were the tuples of y and x coordinates that we generated previously, and yx order because the documentation says so. So now based on the graph, based on the list of nodes and then adding this origin point and destination point that gets visualized in a bit different way. We have the shortest path in this network from origin to the destination. So this is, of course, there's a bit of this conceptual and computational stuff to understand, and then just how to use these OSM and X functions and network X functions to actually get the routes, get the source data, get the origin and destination points from there. So this is, of course, now a tiny area, but we could then route from Helsinki to Rovaniemi in the drivable network, or from Kumpula to Löyly in the walkable network. Or bikeable network. I think I'll take a tram, but anyway. So is there some questions? You'll repeat again all these steps in the exercise, so that's the best way to learn these. And again, here we have been reading a lot of the documentation, which is then a key when you're wondering what data types do I need to pass on, and so on. What are the requirements for this particular function? So then the latter part of the tutorial, again, there's all the code typed in. And we can go through some of the rest, for example, how we can then save this path, for example, as a shapefile. But in here we're first from the geodata frame getting all those based on the index where the route IDs are. So these are then the actual points, shapely points, and the whole geodata frame, which represent the nodes of that path or the shortest route. Then, as we have done before, we can pass a list of those geometries to the shapely line string, make a line out of it. So this is now the same line as this shortest path in here. And it is still in this projected coordinate reference system. Then we do we are doing some length calculations. So basically repeating the stuff that we have learned already in this course. We have if we then have a line string, we can create a geodata frame based on that line string, add some columns, kind of attaching the OSM IDs from the root nodes to there, and then based on the geometry, calculate the length of this path. And now that this is important that the data is in the projected coordinate reference system so that the length calculation makes any sense in a metric. Now this is in meters. And there we're again fetching the buildings in order to then plot these together on a common map. So in this week's exercise, you don't need to make any fancy plots. That focuses in week's 5 exercise, but then of course you could use these in further visualization purposes. And then finally, we can store all the data here. Now we are storing shape files. So, and also there's some tricks we're doing with file paths. I was thinking that I'll maybe next week when we have the QGIS plugin tutorial, then the latter part of the lesson, I could repeat some of these central things, such as playing with file paths. So let's come back to that then. But basically here we're defining file paths for these different feature types, and then just this is a geodata frame to file and then file path, and getting those onto the disk. But also these steps we don't directly need in this week's exercise, but if you need that later, you can then check those code cells in there. So the core learning goal here would be then that you are able to kind of find whatever input, origin and destination you have. You're able to find the nearest node in the network and then do this based on then the shortest path algorithms. Find the shortest path and maybe visualize it on a map. But the exercise, I hope these links work. Now there's two problems where you get to go through the central parts of this lesson, and you'll need to read the OSMNX documentation. So the page that looks like this, and use some of the a bit different variations of the same functions that we used in the lesson. So you can also practice reading the documentation in this exercise. Where was I? Here. So problem 1, we are here then working with input files. So there's origins and destinations. And the first task is actually, well, not related to this week's lesson, but previous skills. So you should first figure out where are these points from. And how would a geographer do that? Well, we would visualize them on a map. So there's latitude and longitude coordinates. So you can plot the points on the map, for example, on top of a static base map, or why not an interactive map, for example, using MPL leaflet. So just a few lines of code. And then there's option B. So do both of these just to practice. So we can reverse geocode these points to get the address or the city or the state. So these you should already be able to do, but just to refresh your memory. And as an output, you'll get a city somewhere on Earth. That is the answer. And then we'll do the analysis from this particular location. So then we will fetch OpenStreetMap data, the street network from this place, and for that you'll need to specify the extent. Extent for downloading the data. So in the exercise, the input is a set of, we only have the points, running out of space. So you have some origins like this, and then you have some destinations. And that's it. And then you should define a polygon for these origins and destinations. So one way to do is that you combine them and then you make a convex hull, or then you could take a bounding box for them. But then the problem is that some of the routes might go like this, so beyond the extent of the points. So then you should add some type of a buffer to the extent of the input points when defining the polygon area. So there's I added some hints to the hints page on this, and use the help of Sara and Sakke on Thursday. So this is maybe the trickiest part of the whole exercise, but it kind of combines then the skills we have learned earlier in this lesson. So combine the points, define a polygon with a little extra space so that the routes might go like beyond the extent of the points in this step. And then we use this OSMNX tools for fetching the graph, again, only the drivable network. And then we reproject the data. So we have these kind of expected outputs plotted already in here. And then in problem 2, you'll do routing between all origin points and all destination points. So that's kind of a bit similar approach that we have done in the travel time matrix. So we have calculated routes between 13,000 grid centroids. So there's 13,000 times 13,000 routings that have been done. So here you will do then from all the 16 points to all the 20 points as an output. So it will look like this. And then actually we have, I hope this is now correct. So the kind of to spoil the fun, we have the correct answer in there. So you can test if you get the same answer as we did. If you don't get exactly this 2,477 kilometers as total distance, if you would go through all these shortest paths, then don't panic. It might be that then there's some you took the walkable network, or there's some tiny detail why your solution is a bit different. So if that's the case, come to the exercises or ask in Slack what did I do. So then it might be just some tiny input thing. So here we didn't want to flood this exercise with too many instructions because it's the last exercise, so should also be a bit challenging, but I think it's quite a fun task in a way. And well, now I set the deadline again to next week's Wednesday. So let's maybe check on that next Monday, just to then allow again enough time to check the weekly exercises before Christmas, so you get the feedback from those already before Christmas. But if this, I know everybody's busy with other courses as well, so if we need to extend the deadline, that's also fine, because this is now indeed the last exercise before the final assignment.